Welcome to the Northwest Geology Guy. My name is Scott, and today we're going to talk about how a stratovolcano works, like around the Ring of Fire, especially in the Cascades of Washington, Oregon, and California, and bring you guys kind of up to date on what they've discovered and how the old theory of magma chambers just doesn't work anymore. But here you can see kind of a cross-cut section of the subduction zone. As the ocean floor subducts down underneath North America, not only does land subduct, but it also allows water to enter in along with it. And what the water does, it superheats and helps dissolve and melt the crust and thin and heat up the magma. So it makes it easier to rise to the surface. This is a really good illustration because you can see the water here also entering down in the transformation zone. But let's go ahead and take a look at the other photo and we'll get more into it. Okay, here is Mount St. Helens, and the conduit comes down into the upper magma chamber, which sits only a few kilometers underneath the mountain. Now, typically, in the old graphs, it would show the volcano, the conduit, and a round magma chamber, kind of looking like a thermometer. But that's not really what they've been finding under the surface. But this is where the semi-melt is down here, and in the lower section is the larger magma storage zone, the lower magma chamber. There, the temperatures are a lot hotter and more fluid than what you find in the upper chambers. But when there's a large water intrusion with the magma, it tends to start to dissolve this and heats it up and sends the heat up here to the semi-melt, liquefies that. It starts to degas with the water. Water also helps it degas, and then sends it up here through the conduit up to the crater. And I'll show you what happened later on when just prior to the May 18th, 1980 eruption, you could see how much the pressure was building in the mountain. Now here's a prime example how pressure from degassing and the pressure from the magma coming up, the conduit has no place to go. So it will pick the easiest and weakest area of the mountain and create a bulging effect. Sometimes it will just come through a small dike up here and erupt off the side. That's very common in a lot of volcanoes. You'll have more than just one crater. And but here, Mount St. Helens had a big weak area on the northern side of the mountain that grew about an average of 5 feet a day. And that's a heck of a lot of deformation in just one day. And that continued on until finally it reached its breaking point. A 5.1 magnitude quake struck, and this whole north section of the mountain gave way in what was to be the largest landslide in history, recorded history. So, and then the lateral blast that came out afterwards blew down hundreds of square miles of timber. Prime timber was just turned into like giant toothpicks, pointing all away from the mountain. Every one of them was blown down away from the mountain. And that was, they expected a vertical blast. But some of the USGS guys knew what was going on. They were monitoring the cracks in the volcano, and they were starting to see that this is not going to be a vertical eruption, but a lateral blast. And that's exactly what turned out to happen. I was only 18 at the time, and I was just fixated to the TV news, watching every second I can on any channel that had it on. It really interested me, since this is in my state, and this is going to be my first volcanic eruption to witness. But that's how that happens. But now let's get into the mechanisms. Okay, I lied. I forgot I had this slide up. But here's a side view of the lateral blast that occurred after the landslide came down. And down in this area here, that's what they call the pumice plain. That's where all the pumice from the volcano ended up down here. If my body was in better shape, I would love to go down, hike down there, and pick up some samples of the pumice that was left behind. Pumice is so light and so full of air holes that you can drop it in water and it will float. You stick a normal piece of lava into a water and immediately it sinks to the bottom. But I just find it really cool. But that's the last slide on that. It shows you, and after the lateral blast became the vertical blast that reached elevations of 80,000 feet in the atmosphere and traveled around the globe many times. But I just wanted to go ahead and show you a picture of that, let you see what had happened if you haven't already. Well, real quick before I go on, here's another slide I found showing the vertical blast. Here, it looks like it was taken from the northwest side of the mountain. That shows the vertical blast that went up to 80,000 feet. During this, the mountain lost about 1,300 feet of the summit that was blown away along with the north face of the mountain. And this is what it looks like down here today with a big horseshoe crater. You can still see how the debris flowed out the mountain down here and filled about 200 to 400 feet of lahar and ash deposits down here. Before it was a little deeper valley down here. But it was pretty devastating to watch as the lahars were coming down and wiping out bridges. There was one picture of a house floating down, the entire house floating down the Toutle and smacked into one of the steel bridges there. I can't tell you, man, I was in such awe watching that. That's the power of Mother Nature. Okay, now to the meat of the video. This is kind of more like what the magma chamber and the magma reservoirs look like underneath Stratovolcano. You have the conduit that comes down into an upper magma chamber, and magma will flow horizontally away from the volcano, like in St. Helens when they did the IMUSH study. That's imaging the magma under St. Helens. And they found that the magma chamber wasn't just a little kind of bowl down here underneath the mountain, but it stretched out vertically quite a ways, and then it went out and looks like it's connected to Mount Adams, which is just to the east of it. And I apologize, I couldn't find the image for that. I've seen it before many times, but I just couldn't find it this time. But it showed you kind of a graph like this, ultrasound image that showed it to go all the way out east to the Mount Adams, which I'm not sure why this has remained so active and it hasn't really flowed to the east. Mount Adams hasn't gone off in many years. And I just found that kind of interesting, how this has stayed so active over time, and Mount Adams has just remained quiet. But the IMUSH study used like soup can size seismometers, and they used thousands of them all around the area of Mount St. Helens, out to, I think, 5-10 miles. I can't remember how large the radius of it was. But since scientists know how fast a seismic signal travels, what they would do is set off a controlled explosion and measure the time that it took to get from point A to the rest of the seismometers. And they could tell when the signal was going through liquid, either magma or water, because it slows down as it goes through a liquid or magma like that. So they know, that's how they mapped out the chamber, kind of like what they did at, actually pretty dang close to the way they did Yellowstone's magma chambers, and found out that geez, we have a way bigger magma chamber than what we had anticipated, because it will fill up the Grand Canyon 11 and a half times over. And that is a heck of a lot of magma stored under the ground. And that's why that's such a dangerous volcano. And everybody talks about Yellowstone going to erupt and stuff. But that's why I like Ben Ferriolo and Mary Greeley. They don't usually talk too much doom and gloom. Ben doesn't. He goes by the science and what the science tells you. Same way I do. I won't make up anything that I don't know. There's been many things I wanted to report on, but I just didn't have enough facts to support my theory of what was going on. So that's why you don't see those. I will tell you when something is my theory or my thought. Like my theory, it's starting to kind of prove itself, but still a long ways away from being 100% true. But since the Cascadia, or the Juan de Fuca, the Explorer, and Gorda Plate subducted a northeastern angle under North America, that since it goes down in the sheet, that it would melt and come up in a sheet that would connect all the volcanoes together. But my buddy Wes down at USGS in Vancouver, it's a CVO, he thought, well, he told me, he says, that's an interesting theory. He goes, but we really don't believe that that's the case. But I said, only time and further studies will prove one way or another. But he did say that it was a very interesting idea, but we'll see how that works out, because as they're doing more studies like this, like the IMUSH study at St. Helens, and he told me like over a year ago, they're planning on doing another seismic test like this too. Excuse me. And, excuse me, I guess a little bit of a cold still. But I'm thinking that that's the way it may turn out. It may not be totally one big curtain of magma, but I think they're all connected horizontally. But I do like the way this is set up here. It shows you the areas here, like the little dikes that come up. They're also known as feeder dikes. That played a big part in the Columbia lava floods over in eastern Washington and in Oregon. That these dikes opened up here and created fissures that opened up and spewed out a massive amount of lava, of basaltic lava. Because the only way that the lava changes from basalt is if you want to call it like a default type of magma that comes up from the mantle. The only way it changes into rhyolite, diacite, is that it goes up through the crust that is loaded with silica. And the more silica it picks up, the more viscous it will be, more thicker it will be, and it changes from basalt into like rhyolite and stuff like that, depending upon the content of silica. Now, basalt is only about 45% silica. Rhyolite, which is very dense and doesn't degas very well on the way up, so it tends to be explosive, like Mount St. Helens. That's made of rhyolite. And basalt is very thin in comparison to the rest. It's the thinnest on Earth. And it'll start degassing, and that's what caused the bulge, is the degassing of the magma as it was coming up. And it's like shaking up a 2-liter bottle of pop and then opening the top. All that pressure, because when you shake a bottle of pop up, the CO2, the gas part of it, starts to separate from the liquid. And that's why you get such a violent explosion. If you shake it up real hard like that, then open it, it just starts shooting out. Well, that's kind of how a magma or a volcano here with a magma, when you have a lot of magma that's not degassed very well. So when it comes up here and it finally breaks the surface here, if it has enough force behind it, it will just shoot out of the mountain and create a big ash plume, pyroclastic flows that will come down the sides of the mountain. And that's basically how a volcano works. Now, sometimes, like I told you here, a little vent that will pop out, a little dike will occur up here and create a vent here, and have an eruption through here. Etna's done that. Etna has 3 or 4 cones, but the magma wants to come up like a beach ball under a pool. You press it down and you got so much resistance because it wants to shoot up out of the ground. But excuse me about that. But it wants to shoot up because of the pressure from the air inside. Same with the magma. Now, over in eastern Washington, I picked up a lot of samples of the different colored lavas and stuff as I would find them as we'd travel around. And you can just see the gas holes that it left behind in the sample of the lava. And you don't get that with diacite, rhyolite, andesite. They don't have the gas bubbles because it's already expelled or locked deep inside. But I really hope you guys learned a little bit today on how a volcano works. But please feel free to leave a comment, ask any questions. Remember to subscribe if you're new. But I hope you really enjoy it, and I look forward to bringing you more interesting videos in the future. All right, good night and have a good evening.